Hello everyone, welcome to online video lecture series developed by Jawaharlal Nehru Technological University Kakinada in association with Andhra Pradesh State Council of Higher Education. This is Dr. M. Prem Kumar, working as professor in the Department of Electronics and Communication Engineering, Sri Vishnu Engineering College for Women, Bhimavaram. Welcome to online lecture series. Today's class we will discuss about transfer function of a LTI system. Generally, continuous time LTI systems characterized by its linear constant coefficient differential equations. Continuous time LTI systems characterized by linear constant coefficient differential equations. So that is CCDE. Nth order system can be characterized by differential equations, summation d by dt power k, d power k by k y of t. So here k is equal to 0 to d power k d by d power k by dt power k x of t. Where x of t is a of t is output. So in order to simplify this differential equation, we have to apply Fourier transform on both sides. In last chapter, you might have studied about Fourier transform. So in that one property of Fourier transform, differentiation by dt of t is having a Fourier transform x of j omega. And what is the Fourier transform? D by dt of x of t. Omega into x of j omega. You might have solved this. Now, by making use of this differentiation property, we will try to simplify this. Apply Fourier transform on both sides. Fourier transform of summation ak d power k y of t is equal to summation k is equal to 0 to m dk d power k x of t. Continuation to this property d power n by dt power n x of t should have a property of whole power n by x of j. Simply because ak and bk are constants, and we can make use of this summation ak k is equal to 0 to n d power k by dt power k will have j omega whole power k. This is y of j omega. This will be equal to summation k is equal to 0 to m p power k and j omega whole power k by x of j omega. So from this, if you take j omega common left hand side, summation k is equal to 0 to n by n jk j omega whole power k, which is equal to x of j omega summation k is equal to 0 to m ek j omega whole power k. Now y of j omega by of j omega is equal to dk j omega whole power k, where k is running between 0 to m by summation ak j omega whole power k, and k is equal to this y of j omega by x of j omega is defined as h of j omega, which is transfer function of LTI system. And observe this h of j omega is a rational function. It is a ratio of polynomials in j omega. The coefficients of numerator polynomials are the same coefficients or those that appear on the right hand side of the equation. The coefficients for the denominator polynomials are same coefficients as appear on the left hand side. Hence, the frequency response for the LTI system characterized by h of j omega. H of j omega can be treated as a frequency response of LTI system, which is nothing but y of j omega by x of j omega. And consider an example here. Consider a stable LTI system. Stable LTI system characterized by its differential equations. Differential equation. So given by d by dt of y of t plus a into y of t, which will be equal to x of t. A is greater than 0. So we have to calculate the frequency response of the given stable LTI system. Apply Fourier transform on both sides. So x of t will have Fourier transform x of j omega. Similarly, d by dt of x of t will have Fourier transform of j omega into x of j omega. Differentiation property. Now this is j omega into y of j omega plus a into y of j omega, which will be equal to x of j omega. Now you simplify this equation, take y of j omega common, is equal to a plus j omega equal to x of j omega. So frequency response h of j omega is defined as y of j omega by x of j omega, which is nothing but 1 by a plus j omega. Now from this you have to calculate, this is the frequency response. This is the frequency response of a given stable LTI system. Consider another example. Consider a stable LTI system. Stable LTI system characterized by its differential equations d square by dt square a of t plus 4 into d by dt of y of t plus 3 into y of t is equal to d by dt of x of t plus 2 into x of t. Asked you to find out the impulse response. Impulse response. So from the given differential equations, first you have to find out the frequency response. Apply Fourier transform on both sides. J omega whole square A of j omega plus 4 into j omega into y of j omega plus 3 into y of j omega equal to j omega into x of j omega plus 2 into x of j omega. You take y of j omega common in the left hand side. This is j omega whole square plus 4 into j omega plus 3. Now x of j omega common in the left right hand side. So this is j omega plus 2. So from this you can write h of j omega equal to j of j omega by x of j omega, which will be equal to 2 plus j omega by j omega whole square plus 4 into j omega plus 3. So this is nothing but the frequency response of the system. Response of the given stable LTI system. But he has asked us to calculate the impulse response. So in order to calculate the impulse response is represented with h of n, and from this h of j omega, we have to take the Fourier transform, inverse Fourier transform of h of j omega is nothing but the impulse response. Now how to take the impulse response? By taking the inverse Fourier transform. Given h of j omega, factors for this 2 plus j omega by 1 plus j omega into 3 plus j omega. By simplifying the denominator, we end up like this. So using a simple partial fraction expansion, 1 plus j omega plus b by 3 plus j omega. Because we know that x of t is having the Fourier transform x of j omega. So x e power minus at u of t will having the Fourier transform 1 by a plus j omega. By simplifying this a and b values, we can calculate impulse response h of t. H of t is equal to, after simplifying this a and b values using partial fraction expansion, a is nothing but 1 by 2, b is nothing but 2. So this is half into, this is like 1 plus a 1 plus j omega. So a value is 1. So this is e power minus t u of t plus half into e power minus dt u of t. So final equation half into e power minus t plus e power minus 3t into u of t. This is the impulse response of the given stable LTI system. For the same problem, if x of t is e power minus t u of t, then what will be the response y of t? So from the previous problem, we have simplified this h of j omega, which is given as 2 plus j omega by 1 plus j omega into 3 plus j omega. So we know the equation for phi of j omega is equal to h of j omega into x of j omega. So x of j omega, you know, x of t will have Fourier transform x of j omega. So e t u of t will have Fourier transform 1 by 1 plus j omega. So now you calculate y of j omega equal to, what is h of j omega? This is 2 plus j omega by 1 plus j omega into 3 plus j omega into x of j omega is 1 plus j omega. So if we simplify this, this becomes 2 plus j omega by 1 plus j omega whole square plus j omega. So in order to get the response y of t, we have to calculate inverse Fourier transform of the previous equation. So by making use of the partial fraction expansion, we can calculate this. So y of j omega is equal to a by 1 plus j omega plus b by 1 plus j omega whole square plus c by 3 plus j omega. After simplifying these ABC values, a is equal to 1 by 4 and b is equal to 1 by 2 and c is equal to minus 1 by 4. So you can have this y of j omega equal to 1 by 4 to 1 by 1 plus j omega plus 1 by 2 1 plus j omega whole square minus 1 by 4 by 1 by 3 plus j omega. So by applying the inverse Fourier transform, we can write like this. This will have 1 by 4 e power minus t u of t straight away. Similarly, this minus 1 by 4 e power minus 3t u of t. Now coming to this differentiation property, this is 1 by 2 t into e power minus t minus t u of t. So if we simplify this, so y of t is equal to 1 by 4 e power minus t plus 1 by 2 t into e power minus t minus 1 by 4 e power minus 3t into u of t. So applying the inverse Fourier transform, we can get back the frequency response.